Hello, my name is Stein Nesbakk and I am an application engineer here at Nexperia. In this quick learning video we will go over the benefits of low QRR devices in motor control applications. At my top right here we have a standard three-phase drive circuit. We have 6 MOSFETs, 3 on the high side, 3 on the low side, together with the 3 phases which are signified by inductors. This circuit itself is fairly hard to analyze as is, so what we've done is we've just simplified it, taken one phase and even taken off the low side MOSFET, leaving the body diode. The reason for this is that the body diode is the only parameter we're actually interested in. Now, initially when you turn on the high side, you have the blue line, which is the current flow, flowing through the inductor, resistor and down through the ground path. When the high side then turns off, the current will still want to push that same current through, which it will. It will push it down through the resistor, up through the diode and suck it back through the circuit. What happens in the diode is that there will be free charge carriers developing, and when then the high side turns back on, those free charge carriers, they will be free to move anywhere. And as the current then is coming down, you will have the blue line as before, going through the inductor. But you will also have the IRR flowing through the body diode with those free charge carriers pushing through the diode. This effect can be seen on this picture here. You have a red line and a blue line. The red line is a high QRR device and the blue line is a low QRR device. A high QRR device, as you can see, has a larger current spike and a larger ringing. The ringing comes from the QRR and PCB stray inductance working together to oscillate and pushing current back and forth. While with a lower QRR device you have a lower spike and you also have lower ringing. What's interesting is that this ringing, if measured with a spectrum analyzer, it will actually show up there. So here's a picture of radiated emissions of a motor drive circuit. This is with only one phase active, and is comparing a low QRR Nexperia device to a high QRR competitive device. The two devices are very similar, nearly identical, besides the QRR value. That's the difference. The Nexperia device has a 50% lower QRR. As you can see, in the TV and radio band, the Nexperia device is 10 dB lower. In an application, without adding any extra circuitry, that's a considerable amount to drop down by. However, another solution is to just add a gate resistor. And as you can see here, that's a standard solution for industry. And what we then do is that we have a dV by dt, that's when the high side MOSFET turns on. Ideally, you want the white line. However, in the real world, you will have more like the red line, which is a slight inclination. If you then add a large gate resistor, which will indeed lower EMC emissions, you will then have something like the blue line. However, under each of these lines, you have a certain area, and the larger this area, the more power will be dissipated. The more power dissipated means the more heat output will be made. Therefore, adding a large gate resistor, although lowering the EMC, may generate thermal issues. And that's why picking a low QRR MOSFET, which does lower EMC to a certain degree, also allows you to have a slightly sharper rising edge, which also reduces the heat output, not by adding any extra components, just by picking a lower QRR device. So, just going over what we've discussed here, EMI can reduce by several factors. You can add a gate resistor, which slows the MOSFET turn on at the cost of increasing the heat output. You can add filtering circuits, which increase the BOM cost and the board space needed for the design. Or you can just select a low QRR MOSFET, allowing for a faster MOSFET turn on and reducing the heat output without many downsides of it. Thank you very much. I hope this quick learning video has been helpful. If you have any more questions, please go to nexperia.com. Thank you.